that is the mean diameter of that bolt. And based on that, we can go for the selection of any standard size of that bolt. Later on, while we are going to solve the problems, at that time we will come to know that how we can go for the standardization of that bolts and how we can select that standard bolts from the available chart. Now next is that if the bolt is undergoing for the shear, then in that case, how we can go for the calculation of the size of that bolt. Now, sometimes the bolts are used to prevent the relative movement of two parts. That is nothing but sometimes we are going to use the bolted joints for connecting two uh, parts which are pull against each other. That is nothing but here I will draw the diagram. You will understand it what it means. If suppose we are going to have this one plate and if the other plate is connected to this plate, around that welded joints are also used for this. Now, if these two plates are connected and if we are going to use bolt here, nut and bolt arrangement, if you are going to use, in this case, if suppose this is nut and bolt and these two plates are undergone for the stress, that is the tensile stress, if the tensile force is applied on these two plates, that is what the bolted joints are used for. That is nothing but sometime to transmit the tensile force. And these are the force. Okay, this is the force which is applied, and if suppose we are going to use the bolted joint here to connect these two plates together, then this definitely bolt will undergo to the shear. The shear stress should be avoided. That is, we have to design the dimension in such a way that we have to avoid the shear stress failure of this type of nut. Now, it should be noted that when bolts are subjected to direct shear load, then they should be located in such a way that the shearing load comes upon the body, that is the planes which we are going to join together, okay, of the bolt and not upon the threaded parts. That is nothing but when we are going to design such type of joints at that time, the plates or plate thickness, they should not cover or they should not come across the threaded parts, because you know that in case of threaded parts they are more weak because stress will get concentrated over there, sudden change in area is there, that's why stress will get concentrated. And if the stress concentration is there, definitely the shearing will occur at that place. That's why we have to keep that threaded part as far as possible away from the plate thickness. Okay, that means direct shear should not come on that threaded part. Getting me? And at that time, when we are going to calculate the dimension of the nut and bolt, so definitely we have to use the formula that the shear stress, which is denoted by tau, is equal to force divided by area. Now the force which we are going to consider, this force we'll consider as a shearing force. We'll denote it by P, suppose, yes. This PS force which is applied on the plate, that PS force divided by area of this bolt. Definitely area of this bolt will be pi by 4 small d. We are going to consider major diameter or diameter of that bolt. Okay, so pi by 4 small d square, that will be the area. But if suppose we are going to use 5 volts over there for sustaining this PS load, then this P load or P suffix S load which is sustained will be sustained by means of 5 volts, right? So the area while we are going to consider, it should be multiplied by 5. So this force divided by area pi by 4 d square number of multiplied by number of bolts which are used. So we'll call number of bolts as N. So the force divided by area is equal to stress. So force divided by area is equal to stress calculation which we have done. That we are going to calculate for the force. Force is equal to stress. Here stress is denoted by tau multiplied by area. Okay. So area is pi by 4 d square multiplied by N. So this force which will be sustained by means of diameter d and N number of bolts having relationship in this way. Okay. And if the tau is the permissible shear stress in the material from which the bolt is manufactured. This equation can be converted for the calculation of diameter of that bolt. So d is equal to under root 4 PS, that is shear force, divided by pi tau N, where tau is the shear allowable shear stress, N is the number of bolts which are used, pi constant, P suffix S is the applied shear load. So this is what the formulae which we can use while we are going to consider or design that bolt for the shearing or design of that bolt against the shear. Okay, any doubt? Any doubt related to this? You can write in comment box if you had a doubt, or if not, then we'll move further. Hello?
No, sir.
No. Okay. We'll go further. Now we are going to consider combined stresses. Now this is the real case, real situation where the stress for which the bolted joints are designed for the combined tension and shear stress. We cannot say that we have designed our bolted joint only to shear. Sometimes we are going to design it for the sorry for the disturbance. Now this is for the actual situation where the combined tension and shear stress are induced in that joint. So when we are going to consider this combined shear stress and tensile stress, at that time we have to use either maximum shear stress theory or we have to use maximum principal stress theory. Okay. Out of that, we have to use either one or we have to check both, and then afterwards we have to decide the dimension of that bolt. That is nothing but diameter of that bolt. Okay. So first of all, we'll see that what the maximum shear stress theory is. So maximum shear stress when the failure is occurring because of the shear, and if the part is undergoing for the tensile as well as shear stress, then the maximum shear stress is given by 1/2 under root tensile stress square plus 4 of the shear stress square. This is what the maximum principal stress, maximum shear stress theory or principal shear, it will get confused. So maximum shear stress theory, and this is maximum principal tensile stress theory. That is principal stress theory. Okay. So this principal stress or tensile stress is given by maximum principal stress is given by tensile stress by 2 plus half under root tensile stress square plus 4 of shear stress square. So here these two formulas are already we have derived, we have seen in chapter number 1. Now we'll use these two formulas and we'll calculate the dimensions of that bolt, and later on we'll find out the other dimensions of that bolt. That is, first of all we have to calculate the diameter, and then afterwards we will find the other diameters and the dimensions of that bolt. So in this case, as we are going to calculate the shear stress, okay, so in case of shear stress, how we are going to consider the shear stress? As per the previous formula, this value of shear stress, will I write? In this case, this maximum shear stress is given by force divided by area. A value of this tau we are going to put here, and we are going to calculate the tensile. This tau max is equal to force divided by area. So again, this is given by force we are going to denote by P divided by pi by 4 pi by 4 d square. Okay. By means of this formula, we are going to calculate the value of D. And here we are going to take this maximum shear stress by means of this tensile stress and shear stress values. Later on, when we are going to consider the tensile stress, same formula is used. That is, instead of this tau max, we are going to use this sigma T max. And value of sigma T max is calculated by means of this theory. And here we are going to find out the dimension D. Okay. Any question? If you have any query, you are free to ask. If not, we'll go further. I'll see one example. Okay, this example will be solved in one step only. These type of simple examples may not be asked in exam, that is in university question paper, but they are good for the understanding purpose. These type of examples may be there in GATE. So here example is that an eye bolt to be used for the lifting of load of 60 kilonewton. A bolt is eye bolt which is used for lifting of 60 kilonewton force. If you want to draw the diagram here of eye bolt, this type of bolts are there and are called as eye bolts. Okay, here threaded part is provided, and here you can use the hook, crane hook, and you can lift that part. Okay, so here this type of bolt is used, and in this case the force which is applied is the tensile force, and that has a value equal to 60 kilonewton. Okay, and we have to find out the normal diameter of bolt if the tensile stress is not to be exceed than 100 megapascal. The allowable tensile stress in this bolt is given by 100 megapascal. Assume this coarse threads, that is nothing but we are not dealing with the coarse thread or fine thread or any type of other threads. We are just want to calculate the diameter. Okay. So we know that tensile stress is equal to tensile force divided by the cross-sectional area which is undergoing for the tension. So we are going to consider this diameter as a D, okay, normal diameter small d, and we are going to consider D suffix C as a core diameter. Okay, so how we can calculate this normal diameter and core diameter? First of all, we'll consider the core diameter. Okay, and from that core diameter we can calculate the normal diameter, as already we are knowing the relationship between core diameter and normal diameter, that is D suffix C is equal to 0.85 of T. Okay, that we have seen in first lecture. Now this allowable shear stress is equal to force is 60 kilonewton. We'll convert it into Newton. So 60 into 10 raised to 3 divided by area. So cross-sectional area we are going to take on other side, and allowable tensile stress is 100 megapascal. So 60 into 10 raised to 3 is equal to pi by 4 d c square into sigma t, allowable shear stress, and it is 100 megapascal, that is 100 into 10 raised, sorry, 100 Newton per millimeter square. So that we'll get this core diameter as a in millimeter. So this core diameter is given by taking all other terms to this side, that is 600 into 10 raised to 3. It should not be 600 multiplied by, okay, 100 is divided by the 100, and that's why it has been taken as a 600 into 10 raised to 3 divided by 78.55, and that is coming as a 764. Okay, so when you are going to take root of that 764, it is 27.6 millimeter. And once you calculate the core diameter, then can you give me by means of which we can calculate the major diameter? D is equal to how much you will get? D is equal to 27.6 divided by 0.85. So your calculator, can you give me this? How much value you are getting this? 27 by
32.4.
32.4. So we are going to get the major diameter as a 32.4 millimeter. But we are not having this 32.4 millimeter as a standard dimension of the bolt. So M12, M15, M20, M25, M30, M35. Have you heard these names? These are nothing but the bolts which are used. And this M is for the indicating from which material it has been manufactured. M13, that is nothing but a 30 is the diameter, major diameter. M15 means 15 is the major diameter. M4 means the 4 millimeter is the major diameter. Likewise, the sizes in the bolts are available. So we'll choose bolt of M35. Okay, if it is available in the standard table, I will provide you later on. Do you have any question related to this short problem? Hello? If not, we'll go to the next. Now, next part in this bolted joint is that eccentric loading. Okay. Now, there are two types of eccentric loading. One is parallel to the axis of bolt, and another one is eccentric load perpendicular to the axis of bolt. Okay. So we are going to see both of these. Just a minute. Okay. Under can you hear me? Am I audible?
Yes, sir.
Hello?
Yes, sir.
Yes. Okay. Now we are going to see when the loading is eccentric, then how, because the cases which we have seen are just tensile force which is coming on the bolt and shear force which is coming on the bolt. Also, we have seen the combined one, if the combined stresses are coming on that bolt. But when such type of situation is occurring where the bolts are used for connecting a device on which eccentric load is coming, that is nothing but either one bolt is stressed more, other one will be stressed less. Likewise, situation is there. For that, we can consider this situation where these four bolts are used. Okay, now only two bolts are visible here. Four bolts, if you are going to see the cross section on other side, I'll draw here. This is what we can say the top view. Now here we'll say it as a top view. One bolt is used here. Second one is used here. Third one is used here. And fourth one is used here. Okay, this is what the top view is, and the two side views or front view and side view we can see here. Now in this case, the load W which is acting eccentric. It is not directly parallel or in line. It is parallel, but it is not in line with the bolts or the plate which is connected by means of this bolted joint. So in this case, how to calculate the stress that will get induced in the bolts? No doubt that if you are going to calculate the stresses in such situation, at that time we have to calculate the maximum stress which will get induced in any bolt 1, 2, 3, 4. Out of that, any maximum shear stress we have to calculate, and that we have to take for the calculation. Okay. So in this case, if the W is acting which is eccentric from the tilting edge, we'll say this as a tilting edge. Okay. I'll draw it and color it as a red. Now this tilting edge is nothing but where this total component will get tilt, will get move about. That is called as tilting edge. Okay. So in this case, if suppose we are going to consider the bracket having rectangular base, this rectangular base, okay, and bolted to a wall. On wall, it is bolted to the wall by means of four bolts. These four bolts, as shown in figure. Now this figure, in this case, these four bolts are used and it is mounted to a wall. Okay. So here, if we consider, then each bolt is subjected to direct tensile load. Am I right? Because tensile load is acting in downward direction. Same way, this tensile load will be act on bolt 1, 2, as well as 3, 4. For convenience, we'll give name to these bolts 1, 2, 3, 4. These are the visible, that's why I'll say it as a 1. And this is also visible, we'll say it as a 2. This is 3. And this is 4. Okay. So 1, 2, 3, 4 bolts are there. On these all bolts, this W will, because W is pulling down that all bracket. So that is directly tensile load is coming on that all bolts. So we'll say that the tensile load which is coming on each bolt. So it is denoted by W suffix T. and it is denoted by 1 because 1 is indicating that bolt which we have considered is only 1. Okay, is equal to total load which is acting in downward direction divided by number of bolts which are used. Am I right? Because total load is shared by means of 4 number of bolts. Total direct tensile load which is coming. So on each bolt, that load will be equal to W divided by N. That is total load divided by N, where N is the number of bolts which are used. Okay. Now, time to time, we will refer this diagram also. Okay. Now this load W is tending to this plate to rotate, right? Because W is eccentric, and that's why it is trying to tilt the structure in this way. Am I right? And if we take the base as this red line, that is tilting edge, then we'll calculate all the dimensions. Now consider that this L1 is the distance from tilting edge of bolt number 1 and bolt number 3 because they are in line with each other. And L2 is the distance from tilting edge of bolt number 2 and 4. And L is the distance of load which is acting on that bracket. Okay. So this L1, L2 and L, these are the distances from the tilting edge which we have considered, about which this total bracket will get filled. Okay. So as it will get tilt, okay, so the load which is coming on that bolt, that we have to calculate. Now this direct tensile load is coming, okay, and additional load because of the tilting. Because of the tilting, the load which is coming, that is nothing but the because of the movement, the additional pull or compressive nature may be there. In this case, it will be pull, additional pull. Okay, additional pull means tensile load itself. That we have to consider. Now here one more thing you have to understand, that let us consider this W, small w, be the load on bolt per unit length. Now listen it carefully. The small w is the load in a bolt per unit distance, that is nothing but length, due to the turning effect of the bracket. Okay, per unit. I'm saying it as a per unit distance, per unit length. Okay, that small w is nothing but the load, intensity of load, we can say it as, because we are going to calculate it with respect to certain distance. So it is in intensity. So small w is the load in that bolt per unit distance due to the turning effect. Okay. Now this W1, capital W suffix 1 and capital W suffix 2 is the loads on each of the bolt at a distance L1 and L2. Now, as we have calculated, or you are going to calculate that load which is coming in bolt number 1 and 3, that will be same, as well as the load which is coming in 2 and 4, that will be same due to tilting. Okay, so this tilting effect will create additional pull, and that we are going to calculate. So we are going to, first of all, we have calculated the intensity W, small w. Okay, because you know that as the distance from this reference plane, that is red plane, as the distance is going to change of the applied load or the sustaining area, definitely that load is going to get changed. So intensity we have calculated and denoted by small w. Okay. Now, if we are going to calculate that W1, that W1 will be the load which is acting at a distance L1. That will be the intensity multiplied by length, right? So W1 will be the load which is acting on bolt number 1 and 3, and that will be given by intensity per unit length from the tilting edge multiplied by the distance from the tilting edge or length from the tilting edge. Likewise, if you want to calculate the movement of this load, this W1, it will be W1 multiplied by L1. This W1 I have to take as a capital. Okay, W1 multiplied by L1. No, we are going to consider the suffix should not go. Yes. So this W load multiplied by distance, that will be the movement. Okay. So small w into L1 is the load. We'll put it in bracket. This is force multiplied by distance, that will be movement. So it will be small w into L1 square. Getting me? Likewise, we'll calculate load acting at distance L2 and is denoted by capital W suffix 2 is equal to intensity multiplied by distance. And if you are going to take its movement about that red line, we are taking movement at this point. Okay, we'll call it as A and B. So about this AB line, we are going to calculate all the moments. Okay. So this movement of force which is acting at L2 distance, how much force it will be? That will be W2. This W2 will be given by small w multiplied by L2 because small w is intensity per unit length multiplied by length. Okay, that will be the W, capital W 2. So this W2 is given by intensity multiplied by length. And if you are going to take its movement, then movement will be force multiplied by distance. So this is force and is multiplied with distance, and that will be small w into L2 raised to 2 or L2 square. Have you understood this? If you are in doubt, you are free to ask. Should I repeat it or you are clear? Let me know. हे जे आता मी काय बोललो त्याच्याबद्दल कोणाला काही शंका आहे का? हॅलो, हा प्लीज. हॅलो.
हॅलो सर.
हा यस.
बॅकच्या स्लाइड ला जावा.
बॅकच्या साईडला गेलो इथं. ओके.
हा, तो फॉर्म्युला कसा आहे ते सांगा की.
WT1. हा फॉर्म्युला कसा आला?
हा,
ओके, ठीक आहे. मी रिपीट करतो आता. हा जो फॉर्म्युला आहे आपण असं कन्सिडर करणार आहे की एका पेन एक तुम्ही हातात धरला. ओके, सगळेच्या सगळे बोट त्याच्यावर वाउंड करा आणि पेन हातात पकडा. कॅन्टिलीवर बीम सारखा तयार होईल तो. बरोबर आहे का? हॅलो.
हा, यस सर.
येस. त्याच्या एका एंडला W ऍक्ट होतोय असं कन्सिडर करू आपण. हा W काय काय करेल तर आपण हातात जो धरलेला पार्ट आहे पेनचा त्याला मुवमेंट डेव्हलप करेल. कुठं? ज्या ठिकाणी तो पेन आपल्या हातातून बाहेर आला तिथं. इट विल क्रिएट द मुवमेंट, राईट? And second thing, if our hand is too strong and if the force applied is too high, then pen will get shear at the junction where the pen is inserted in the hand. बरोबर आहे?
Yes, sir.
राईट. तर त्यातला जो शिअर पार्ट आहे, डायरेक्ट शिअर ज्याला म्हणतो आपण, हा जो डब्ल्यू आहे, हा डब्ल्यू जो डायरेक्टली अप्लाय केला जातो. इसेंट्रिक आहे ती इसेंट्रिसिटी नंतर बघू आपण, पण हा जो डब्ल्यू आहे तो खाली त्या 4 बोल्टला खाली ओढणार आहे. बरोबर आहे?
Yes, sir.
हा, ती 4 बोल्टला खाली ओढण्याची त्याची जी ताकद आहे ती डब्ल्यू कन्सिडर करू. डायरेक्टली त्याला खाली ओढतोय तो. ओके. तर ती एका बोल्टवर किती होईल? ते एका बोल्टवर होईल, कारण 4 सस्टेन केलाय ना त्याला. समजलंय का?
Yes, sir.
ठीक आहे. आणि काय शंका आहे? हॅलो.
No, sir.
ओके. अजून कोणाला काय शंका आहे? हॅलो. If not, can we go further?
Yes, sir.
Intensity. Okay. This intensity and all that, have you understood it?
Yes, sir.
Okay, so we'll go to the next slide. Now this total movement of load on the bolt about the tilting edge. Now this total we are going to combine together about this tilting edge AB line. That we are going to calculate. So it will be 2 into load on one bolt, that is this movement of one bolt plus movement of other bolts. So why? Because this 2 is used here, because we are having 4 bolts, 1 and 3 of at same line and 2 and 4 at same line. Okay, so the movement of first bolt and movement of third bolt will be same, so it will be multiplied by 2, and movement of second bolt and fourth bolt, that will be second movement. Okay, so we are going to take this movement together. That will be 2 into W L1 square plus 2 into W L2 square. This is first equation. Now the movement due to the external load W which is acting, that will be equal to W into L. Okay, so from this equation 1 and 2, what we can get, this total movement, that should be equal to the movement at first bolt or first and third bolt and second and fourth bolt. Okay, so this W into L is equal to twice of W L1 square plus twice of W L2 square. So intensity here we can calculate as the external load which is acting into its distance divided by L1 square plus L2 square. From this we can calculate the intensity. Okay. Now we'll call the tensile load which is coming on each bolt, okay, due to this intensity. We'll call it as a WT2, okay, and is equal to W2. It will be given by intensity multiplied by L2 distance, and that will be the maximum one because it has a more distance. So it, when we are going to put the value of small w here, it will be WL into L2 divided by twice of L1 square plus L2 square. Okay, and total tensile load will be the direct tensile load plus the tensile load which is coming because of the eccentricity. That just we have to okay, and we know that this tensile load is equal to tensile stress divided by cross sectional area. So tensile stress multiplied by cross sectional area is equal to tensile load. So this WT tensile load we have to take here and we can calculate the core diameter. Is there any question? Any question?
No, sir.
Okay. So we'll stop here today. Remaining part we'll see. To the next lecture. Okay. I'll
Yes,
take
sir.
present. Yeah, I'll take present. Just wait for a minute.